everybody get a recording? Yeah, ECG recording. Everybody saw something? And that came out better than I was hoping for, and still a little bit nerve-wracking, since as of last Tuesday nobody had recordings, and by Thursday almost everybody had recordings. So that was impressive. I guess the main trick was to jack the gain up to about 4,000 or 5,000, because the size of the signals was rather small. That's nice. Anything else on final projects? Well, I wanted to talk a little bit today about action potential modeling, and the basic phenomena is that most cells have a resting potential of minus 80 millivolts or so, and some cells, if you inject current into them, up to some fairly sharp but not very sharp threshold, will suddenly produce an all or nothing response, which can be in shape something like this, or in the case of a heart cell, in the case of an atrium cell, can be rather longer. And for most cells in mammals, at least, the upswing in voltage is carried by sodium ions. And we talked about this once before. Sodium ions, there's a gradient of sodium ions. So if we have a cell, there's a lot of sodium outside and not much sodium inside, which produces a battery. It tends, and the gradient of the sodium tends to push sodium into the cell. Upswing is carried by sodium ions. The downswing is caused by potassium ions recharging or making the membrane capacitor more negative. And in the case of a cardiac potential, this current is very complicated. There's I don't know, maybe a dozen different conductances, but basically there's a plateau that's caused by a mixture of calcium and sodium ions, and then the repolarization again is mostly potassium current. And we'd like to model this using some sort of electronic system, analog electronic system. Hodgkin and Huxley in 1952 or 53 came up with a set of differential equations to model nerve action potentials. Those have been generalized to a variety of action potentials, and they generalize rather well because they're so flexible. I mean, if you add parameters, you can fit anything. The underlying phenomena here that was explained by Hodgkin and Huxley is that if we look at this on the same time scale, there is now we're going to plot current here. This is now current. There is a fast sodium current inwards. There's a fast sodium current that occurs at depolarization. So there's we're going to talk. I'll talk about this in more detail, but in some sense it's like lighting a fuse. It's an explosion. There's an exponential increase in current because the depolarization opens the channels which cause more depolarization. So there's a positive feedback. And so you push the membrane up towards the sodium equilibrium potential, the Nernst potential determined by these two, by this gradient. You say, wow, that's using a lot of energy. That's a short circuit. It's a high sodium current, but it's self-limiting. The dynamics of the molecule of the channel itself turns the channel off more or less exponentially in time. There's been a lot of speculation about how this works, but the best guess I've heard lately is that you have some sort of channel sticking through the membrane here, and hanging off to the side is kind of a tail with a charge on the end. The channel slams open, sodium comes in, the charge is attracted towards the channel and finally plugs it. So it's kind of a first order reaction that occurs where the molecule turns itself off. So you get an exponential decay of sodium current over some fairly short time. Also, and independently, there's a potassium channel, a separate protein penetrating the membrane, which has a slower onset of current and a slower fall of current that causes the flow of ions back out of the cell, because potassium is high inside and low outside. Potassium current flows and repolarizes the membrane. So there's three separate phenomena here. There's a sodium activation, a sodium inactivation, and a potassium activation. And a couple of guys, Fitzhugh and Nogamo, simplified this in the following way. They said, well, really, we can model this. We can lower the dimensionality. We don't want to have all these variables. We've got four variables. We've got voltage, we have the activation thing, we got the inactivation thing, and we got the potassium activation thing, all of which are state variables. Wouldn't it be nice to simplify this a little bit? So what they did was say, okay, there's fast stuff and slow stuff. And the fast stuff is activating, it depolarizes, and the slow stuff repolarizes. We're just going to simplify it and say we're going to abstract away sodium channels and potassium channels and just say fast stuff and slow stuff. The modeling is barely changed by that. You get all the same phenomena. So what's the use of sodium inactivation biologically? Well, it probably minimizes energy loss. The sodium coming in, sodium gradients 10 to 1, a lot of sodium flows. To maintain any sort of steady state, you have to pump it back out. When you pump it back out, you're using ATP, you're using cell energy, and that costs a lot. Probably between 10 and 20% of your entire metabolism goes to pumping sodium out of cells. That's a big load. So you more or less, depending on your body mass and surface area and a few other things, probably dissipate between 80 and 100 watts. Keep yourself alive. And that means some 20 watts of that is going to just pumping ions. So it's a huge metabolic load. You want to minimize it. Sodium inactivation probably helps minimize the metabolic load by minimizing the number of ions that are flowing. So then the basic model of the cell, to refresh you, because we said this once before, is that we're going to have some resting membrane potential, which is like minus 80 millivolts, in parallel with some membrane capacitance. And the membrane capacitance is the structure of the membrane itself. It's the lipid bilayer. It's the physical fact that this is a thin layer of insulator with charged solutions on each side. It's an electrolytic capacitor. So there's some Rm, some resting potential, and then there's some sodium channels. So there's some RNA in this is inside, by the way. There's some RNA with a potential of something like 50 millivolts inside positive, and then there's a separate R potassium with a inside potential of like minus 110 or something, some such thing. Millivolts.
What is minus 110?
Pardon me?
What is minus 110?
That's the potassium potential. And what happens during an action potential is not that these voltages vary, but rather these resistances vary. Or put a different way, when you reach some threshold, a bunch of channels slam open. When they open up, they're in parallel. Each one has a fixed resistance. They're in parallel, so this resistance goes down. When they close again, the resistance goes back up, and the repolarization is accomplished by these potassium channels that open more slowly and let a current in that recharges the membrane capacitor to minus 90 or so. There's lots of details. There's a pile of stuff that's known about this. For instance, if you were to artificially step the voltage on the membrane by injecting current from outside into the cell and measured the sodium current just after the step, you'd find that INA is equal to some I leak times e to the minus V over VT minus 1. VT happens to have a value of about 25 millivolts at room temperature. Does that look familiar to anybody? What does that look like? Looks like a diode. Looks like a PN junction. For exactly the same reason. It's a Boltzmann activation from a voltage relative to some KT. Right? VT is KT. It's about 25 millivolts at room temperature. Another thing that's known is that if we were to step voltages and measure the potassium current, if we were to step voltages and measure the potassium current, no, we're going to do V versus current here, potassium, we would get something that looks like this. We'd get something that increases exponentially near rest and saturates just above 0 volts. So we'd like to come up with some sort of fairly simple electrical model of this that we could, say, simulate with SPICE, or that we could build out of transistors or put onto an integrated circuit or do whatever we want with. And there's been a lot of work on this. let me tell you a few facts about transistors, although you probably know them already. And that is that, let's say we start out with a PNP transistor. So this is a bipolar transistor, so-called base emitter collector. If we measure some IC through here, and we call this VBE, then the current through here is proportional to some I saturation, some I sat times e to the minus VBE over VT minus 1. Huh. Well, isn't that handy? It has the same form as the sodium channel. And it's pretty easy to see that if you were to then make a circuit that looks like this, this is a bad thing to do. You don't ever actually build this. But if you did build it and you plotted now IC versus VBE, you'd see a nice exponential increase until the smoke comes out of the transistor and it disappears. But if you were to put a small resistor in series with this, then as you changed VBE, you'd see an exponential rise followed by a leveling off at some lower current to a steady value, which looks a lot like the potassium curve. So we could build a potassium channel then that approximates, so we want to approximate this piece here. But we're going to do we're going to get cheesy in a couple of ways. One is we're going to say we're going to shift and scale all the voltages for handiness. We're going to shift the voltages so that 0 volts is resting potential. So we're going to shift so that 0 is the resting potential, and we're going to scale from millivolts to volts. So the amplitude of what we're going to simulate is completely bogus, but hopefully the dynamics are the same. The time, the way the system changes in time is the same. And if we do that, then we can model the potassium circuit there as some it's only got 2 leads coming out of it, right? So we're going to have to then reduce a circuit to whatever it is to just 2 leads, and we can. Something looks like this. This time constant is going to determine the turn-on rate of the transistor. And so as we charge up exponentially here, we can delay the turn-on time of the transistor. And this resistor sets the maximum current through the transistor. So we can replace the variable resistance here with the transistor, and what we're really saying is, oh, we're going to pretend that minus 110 isn't much different than minus 80, and we're just going to set both of these to 0. Because we're going to have a 0 resting potential. Now, as you know, bipolar transistors also have another available polarity, so-called PNP transistor. PNP transistor, if we were to hook up a PNP transistor, negative voltage to the collector, and measure IC as a function of VBE, we would find that as VBE became more negative, we would get a higher current until the system explodes. And we can use a combination of transistors to simulate the positive feedback of the sodium channel. And what we're going to do here is I'm going to leave this over there. What we're going to do is we're going to build a circuit that controls a PNP transistor. Again, it's going to be a two-terminal system. We're going to put a little bit of a threshold in here by putting a diode right here. That gives us a 0.7 of a volt slack before we start turning on this transistor at all. And then that's crude. The emitter side of this is going to have a resistance and then a sodium battery, which is going to be 5 volts instead of 50 millivolts. So it's 100 times bigger. This is going to be outside, this is going to be ground, this is the inside. So what happens as we ramp up the voltage here? As we ramp up the voltage, let's say we were to have a resistor here and apply a stimulus voltage, which is a ramp. Well, pardon me? It's a ramp. As we start up the ramp, this transistor is sooner or later going to turn on and drop this voltage towards 0 here. That's going to turn on this transistor, which is going to make, interestingly, make this point even more positive, drive this transistor further on, which almost instantaneously causes this transistor to go saturated on. So this is the positive feedback mechanism. As soon as you get this voltage going more positive than the diode drop voltage, this circuit slams on and stays on. There's no sodium inactivation here. So this is like sodium activation with no inactivation. What turns the system off? So this module then becomes this module. How would you add sodium inactivation to this? So there's a cheesy way of doing it, which I've tried and it works, and that is to...
What if we flip the battery?
Oh. But then, but then this is biased backwards, right? So what if you did this? So instead of, so you have like a 10K resistor here and a 500 ohm resistor here, and this would be 500 ohms. The battery would trickle charge this capacitor when it was resting. When this whole system is turned on, it sucks the charge out of this capacitor almost instantaneously. And then there's no more charge because the very large resistance here causes such a large voltage drop. So that you can trickle charge, you can have a charge storage. You have sort of a little reservoir of sodium charge, so to speak, on the capacitor. And when you use it up, the system turns off. And that works. It's a little crude, but it works. The dynamics aren't right, but it does work. So if you bolt all this stuff together, where's the remote control? I didn't look for it. That's a mistake. Just slowly fading in here. So if we bolt this all together, so we have the resting membrane resistance, and again the resting potential is 0, so this just goes to ground. There's a resting membrane capacitance. There's the potassium channel. And there's the sodium channel with the 5-volt driver there. No inactivation in this case, just the 5-volt driver. Pair of transistors. This one turns on, crowbars this one on, which then conducts all of the current. And I added one resistor. This resistor causes a very small leak in sodium current at all times.
Why is that used? To represent the leakage in the cell?
So that's actually an add-on I hadn't talked about yet. But if the system is slowly discharging, so we're at rest. We're slowly discharging. We're sooner or later we're going to get threshold. Boom. It's going to fire an action potential. Come down here, slowly discharging again. So this resistor causes the circuit to be a pacemaker. We can show that. Try and get some of the dust off of me before I simulate this. So let's run the simulation here. And it takes a moment to come to equilibrium and auto-scale itself. And I set it up to pace at about 1 hertz as if it were an atrial cell. So it's sitting here pacing away. And you can see the slow depolarization due to the leak. You can see the undershoot here due to massive potassium current repolarizing. Let's modify this cell, that resistor. It's at 100 or 800K. Let's take it up to 1 meg, see what happens to the frequency. The frequency right now is at 2 hertz. It depolarizes, it depolarizes, it depolarizes, it depolarizes, fires an action potential. Finally.
It's just that the charging gets slower.
Charging gets slower. And the auto scaling is croaking on the system. Actually, now it fired once and now it's doing some sort of weird oscillations. So it's not actually firing action potentials then. Oops, don't want to do that. That's a bad idea. So if we set this down to 500K, now the frequency is higher. Charges more quickly, and but the dynamics of the action potential itself haven't changed very much. It's just that it happens more often. And you can play with various things. You can ask, okay, what happens if you modify some? Okay, let's take this and slow down the potassium current a factor of 2 or so. Uh-oh. It's stable at an intermediate value. That's not good. So it doesn't oscillate anymore. So that's not a good idea. So let's take this back down to around 100K and bump this up to 6 or so. 50% bigger. See what happens. Well, now I don't know if you can, how your visual memory is, but this action potential is slightly wider because it's taking longer for this to charge, which means it takes longer for this transistor to turn on, which means that the voltage stays high for longer. So you can mess with the dynamics to a certain extent.
So the values that you had initially were standardized values from the research?
The values I had were ones that oscillated. It turns out that SPICE doesn't do tremendously well on this kind of circuit for the following reason. There are some extremely fast processes because of the positive feedback here, and some very slow processes. That says to get good accuracy, you have to take a lot of little tiny steps. And so the system is ill-posed, if you want, or ill-conditioned. Or in the vernacular, it's a stiff system. The ratio of the fastest time constant to the slowest time constant is big. And most differential equation solvers tend to fail under those conditions, and SPICE is no exception. So you can't necessarily take these values, plug them into a whiteboard with real transistors, and expect it to work. You have to fiddle with it a little bit. You say, okay, our goal here is to build a heart, so we still need one more current to, pardon me? Yeah, the calcium current to make it go. But this is at least a viable model of maybe an atrial cell of a pacemaker cell in the heart. So what we need is a circuit that has the peculiar ability to pull the voltage back down to a fixed value and hold it there. So we need a circuit which turns on a little bit slowly, because the soda is slower than the sodium. But once it turns on, it neither pulls the voltage all the way back down, nor keeps it at the maximum voltage. Well, the goal here was to try and make it all out of transistors. Which after all have kind of a well-defined, but you could do it with an op-amp. Actually, there's another way of doing this whole thing with an op-amp, which I might tell you about later. You run the op-amp in a starved mode so that it barely is biased into operation, and it becomes sort of like a sodium channel.
But if you attach a capacitor and a zener,
you could do that, but that never turns off, right? It might work. Yes, it might work.
I mean, yeah, below the zener's voltage and it will work.
Yeah, so that's right. The solution that these guys came up with, I didn't think this one up. Believe me, I never would have thought of this circuit. So there's an NPN transistor here, a PNP transistor here, going to a PNP transistor here. This base is connected to a resistor to the same point as the collector, which goes to a capacitor to the outside to ground. And you put a resistor here for current limiting. So this is one node. And the other node is here. And where does this go? This is driven from here. Yikes. So let's say we're starting at rest here. Voltage here is 0. You get some non-zero voltage up here as the system starts to depolarize. Both of these transistors start to conduct when the voltage here is about 1.4 volts. They start to conduct at about 1.4 volts because you need about 0.7 to turn this one on, about 0.7 to turn this one on, and this point is at 0. Okay, so nothing at all happens until the voltage gets up to about 1.4 volts. Then this capacitor starts to charge because current finds its way through here. Starts to charge up, keeps on charging up to about 0.7 volts or so. At around 0.7 volts, this transistor turns on and latches this voltage at 0.7 volts. As soon as this transistor turns on, wait a minute, this transistor's on, this one's on, a lot of current flows. And the system then hovers at 0.7 plus 1.4, which is about 2.1 volts. And it stays there until the voltage drops below 2.1 volts, at which time all of the current stops. Because now one of these transistors is going to cut off. This transistor is going to cut off. Because it is no longer 1.4 volts more negative than this voltage here. This voltage falls enough for the transistor to turn off. Once this transistor is turned off, there's not much place for this charge to go, and it just stays there. It actually slowly leaks out through various leakage paths. And so the effect is to regulate the voltage here at 2.1, 2.0, or 2.1 or 2.2 volts, something in that region. If it's lower than that, no current flows. If it's higher than that, these transistors are forward biased and more current flows. So it's a 2.1 volt regulator.
So from the connection, okay, the transistor on the left hand side top.
Yeah.
So the output line has a resistor. No, yeah. So this is connected to the base through a resistor, right? What if that link was missing and this was directly capacitor to the ground?
And where would you put this then? Oh, you're saying to take out this whole thing. Oh, okay. So you know, so that it's charging off of here and not off of both of these. So you can imagine if both of these time constants were the same, then the voltages here would track, except that this voltage would keep climbing. What would happen? This voltage would climb and never decrease because there's no DC path out of here when this. You could get into a situation where this junction is forward biased, which you don't want, right? You could get into the PN junction for the collector and the base always need to be reverse biased. And I can't see how you could guarantee that would always be true here. It seems like these could charge at a different rate. But I'm not. I better not just. I better simulate it and think about it rather than talk about it first. It's too complicated for me to figure out on the fly. But it's a good question. I'll try it and see what happens. So if we now add this circuit, now we have that broke it, huh? Yeah, there's a strangeness here. But you can see that there's a plateau now. There's a little transient overshoot, which is caused by and it varies in size because of the numerical error in the calculation, I think. You can see the sodium current, and then there's a plateau, which is caused by this plateau current. And then there's the strong repolarization due to the potassium, and this is pacing on its own because again there is a sodium leak here. So this is kind of a model of a ventricle cell, and ventricle cells do self-pace. If you take a heart apart with a detergent, spread out the cells, each cell will sit there and beat. Right, it doesn't require any neural input. It's an unstable system, and it'll sit there and beat on its own. So this is kind of a model of an atrial cell with a wider action potential. So then we can ask what happens if we hook this thing together. So now we're going to take an atrial cell model, hook it to a ventricle cell model. So this is the absolutely most stripped down heart you could imagine. It's a 2-cell heart. A pacer connected to a ventricle cell with a rectifying junction. That is to say, it's a diode and some sort of current limiter here, which simulates the bundle of connections going from the atrium down to the ventricle. So this is kind of like what's it called, the bundle of His or something, H-I-S? Bundle of His. That carries information down to the ventricle. And if we run this, if we simulate this, there's a startup transient where everything's weird and everything's auto-scaling all over the place. And then we're almost, but not quite, getting phase locking. Oh, I guess we are getting phase locking now. So for every one of these pulses, we're getting exactly one of the ventricle pulses. So now the system phase locked. It took quite a while to phase lock, you'll notice. It took a bunch of beats to phase lock. If we were to increase this coupling resistance slightly, let's say up to double it or triple it, both sides are still beating, of course, but now there's no particular relationship between them. The coupling is not strong enough to phase lock. You can see the current artifact due to the above pulse. Or is it going to phase lock? No, it's not quite phase locked. So now we have some sort of arrhythmic situation where and depending on the relative beat rates of these two, you can get situations where you have double beats. So you get boom, 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 boom. You'll get very irregular beats. In fact, you can get chaotic beats on the ventricle side. You can get 2-to-1 locking. I'm not sure I can make this do a 2-to-1 lock. But you can get 2-to-1 locking. Let's see. Let's bump the strength of the connection back up fairly high, and then we're going to slow down. We're going to speed the pacer up a little bit. Now the pacer should be much faster. I think it's 2-to-1 locked. So what's this called? This is called a partial AV block. Right, where you have the ventricle beating twice as fast, half as fast as the atrium is trying to drive it. I believe that's referred to as a partial AV block. So the current that's injected off of the pulse where it doesn't lock is certainly affecting the nonlinear oscillator. It's biasing it towards a pulse, but it doesn't have enough current to actually drive it to a full pulse. But it's causing the next pacemaker pulse to have enough current to drive it. So what happens if we speed this up even more? I don't know. I don't know what'll happen. It looks to me like it's. Is it still 2-to-1? It's still 2-to-1. Okay, so let's decrease the coupling a little bit. Still 2-to-1. So now let's decrease the coupling some more. And now we have probably it's uncoupled. I think it's uncoupled. Or it's got a very long period anyway. So One question, which I don't know the answer to, is if you build a whole bunch of these, could you simulate fibrillation? We have desynchronized firing. Could you... What I have done is to build a network of 20 or 30 of these cells, simulated a network of 20 or 30 of the cells, come up with a reasonable model for the impedance of the body, and generated a pretty good looking ECG by doing a linear weighting, linear addition of the various pieces. And you could imagine making this better. You could imagine adding some sodium inactivation. You could imagine getting a little bit better dynamics for the potassium, for fiddling with this plateau current, maybe using op amps to get more accurate. The nice thing about these is that they'd be pretty easy to synthesize on an integrated circuit. And, but they're also quite easy to build on a whiteboard. They're small enough that you can put a few of them on a whiteboard and hook it up and watch what happens. Oh, let's see what happens. Let's take this back more to the defaults. Well, let's leave it like this and see what happens if we remove this diode. Oh, good. Yeah, things you should never do in a let's see if I can actually delete that. It really doesn't like that loop with no resistance. So that's ugly, but it's connected. Now there's going to be some sort of weird feedback here because the current from this guy can affect here. Oh, but the resistance is still pretty high. So let me drop this resistance again so that they're coupled. Oh yeah, look at this. So there's some bizarre atrial rate there now. So, oh, we're getting doubling, twinning of the, not quite twinning. Two, three, 1, 2, 3. That's pretty irregular. But now the current from this guy, the rather large current from here, is feeding back into the atrium, which generally doesn't happen in real life. So that diode is probably a good thing to have there in terms of modeling. You can fiddle endlessly with nonlinear oscillators. It's its own field of endeavor and pretty entertaining. But I think you can, with this, you can show various interesting things. You can show an atrioventricular block. That's what we were showing there. A sinoatrial block, which would be impaired pacemaking. So you leave the ventricle intact, you leave the connection intact, but you start messing with the total drive current available from the pacemaker and watch what happens. I don't know if you can build enough cells to get ventricular fibrillation. You would think that you have to build enough cells so that the characteristic time of circulation around the loop is larger than one action potential time. So you have to have a characteristic circulation time of at least a few hundred milliseconds. So I don't know how many ventricle cells you'd have to have in a loop to do that, but it would probably be several. You can simulate the effect of various drugs by changing membrane parameters. So what does digitalis do? One of the first drugs that was used for heart failure, it was used hundreds of years ago for heart failure, was foxglove. It's a flower, grows in Ithaca. You better not eat those guys. It's a cardiac ganglioside. It's a sodium pump inhibitor. And under certain circumstances, it can cause the heart to beat much harder, interestingly enough. Oh, by the way, do you know that there's a poisonous plants garden at Cornell? You ever been to the poisonous plants garden? It's a whole garden where everything in it is dangerous in some way or another. It's up behind the vet college. It's used for training vet students on how to get animals avoid dangerous stuff. Wild chives are there because it turns out it makes cows sick. Up until the 70s, they had marijuana there. Took that away for some reason. They have the most beautiful poison ivy plant I have ever seen. It's huge. It's beautiful. They have Jimson weed, but also foxglove. You could try and look at channel blockers of various sorts. You could simulate changing the concentration of... Oh, how do you simulate changing the concentration? Well, changing the concentration... Let's see if I can avoid any wires when I do the pinchy operation there. If you were to change the potential of this battery, you would have essentially changed the sodium concentration. And that'll do something to the dynamics, but I'm not sure what in this context because it's kind of a mess with everything going on. But it apparently has changed the dynamics a little bit. There's no longer those extra pulses in there. So you can change sodium concentrations. You could do a lot of biological-like experiments and ask how well the model matches the biology. That would be probably an interesting thing to do. There's no particular reason not to build your own models. Add some transistors. Add a RC. If you added a pair of RC circuits in here, this really eats the batteries on the... That's horrible now. That used to be the potassium circuit, still is. If you added a pair of RC time constants here rather than one, you would get a more realistic potassium dynamic. Nobody's done that. It'd be fun to do. It could be fun to do in simulation, it'd be fun to do in real life, with real transistors, that is. How would you make a chemical synapse? I built an electrical synapse here, which was a diode and a wire. How would you build a chemical synapse? Well, you have to have some more dynamics. Figured out how to do that once upon a time. It'd be interesting to try and make that right. There's all kinds of things to do with it. Anybody tempted by that as a final project? Yeah, but you already have 3 final projects, right? It is fun. It's also fun to then try and build these things and watch how badly SPICE does at simulating real circuits. That's instructive. Any questions on this?
Just out of curiosity, how does SPICE solve these circuits?
How does SPICE solve them? Okay. If it's a linear circuit, it's easy. You can write a Kirchhoff's laws for all of the nodes if it's a linear circuit, and what you come up with is a matrix of derivatives and first order relationships. And pardon me? And it can be inverted, and that's right. Once you've inverted, you've solved it. Once you have a nonlinear element, that doesn't work anymore. So you have a set of nonlinear equations, and the only way to solve them is by iteration at a time step. So the way SPICE works is it makes a guess about the current dynamic state, and then it iterates it until everything is self-consistent. Then it takes a step forward in the differential equation and does it again. And that can be quite time-consuming. It uses Kirchhoff's voltage and current laws to set up the differential equations, and then the static nonlinearities of the transistors and the diodes are modeled in some specific way, which may be more or less realistic, depending on the simulator. For instance, we can ask what parameters are available for that diode, forward voltage, end of story. Transistor, what's available? Well, the forward gain, the forward current gain, HFE. And that's about it. So it's not a wonderful model. That being said, with this particular version of SPICE, you have available a controlled source, a dependent source, and once you have a dependent source for which you can write a relation to any other point in the circuit, you can build anything you want. And one of the parameter inputs of this dependent source is any arbitrary mathematical function of any other voltages or currents in the circuit. So you can build a quite complicated model if you want to go to the trouble. Now, I don't know whether there's more parameters under the covers here that you can't get to, and it wouldn't surprise me if there were. But I don't know how ideal these transistors are. This is, after all, I-circuit. A lot of the details are hidden. Anything else? My current desktop, the desktop solver that I use right now is LT Spice, which is rather more flexible, and it's free from Linear Technologies. You can Google up LT Spice, download a complete version of it from Linear Technologies. It has a detailed model of every part Linear Technologies makes. And then it has generic models, limited generic models of other parts. It has generic op amp, has generic voltage regulators, so on, that you can parameterize and play with. But has quite detailed models of Linear Technology stuff, which is nice. It's good stuff, but it's obviously they're trying to sell their own stuff with their modeler. I used this for the freshman course. Everybody could download a copy except for those poor souls that had Macs, and they could too using Parallels. But it was pretty successful. They could all run it. It made sense to them. Wrote a little tutorial on how to use it, which I can link up for you if anybody's interested. I think the solver here is a little more flexible than the iCircuit solver, but I'm not sure. Yes, you can. You can input waveforms. You can put a WAV file into LT-Spice, and it'll calculate the result as say for a filter. Actually, on iCircuit, you can input the microphone works with the real microphone. The speaker works with the real speaker. If you hook up a buzzer, if you build a buzzer circuit and hook it to the speaker, it makes noise. There's an accelerometer that works with the accelerometers in here, so you can make a tilt-sensitive circuit. So it uses the iPad I/O pretty well. LT-Spice will input from a wave file and output to a wave file. So you can take an animal call, feed it through the LT-Spice simulation of a linear filter, output it to a wave file, and listen to it. That's pretty cool. But it is a simulator. It's not a real time. It's not like LabVIEW. Anything else? What do you want to hear about now? Do you want to hear some more about modeling? Do you want to hear about how to build a synapse, that kind of stuff? Do you want to just go to the lab? We'll start meeting in the lab every day. What's your pleasure?
Is LT-Spice on the computers in the lab?
LT-Spice is on the computers in the labs. Yes, it is. So, and I have a fairly large LT-Spice page that you could download circuits off of, including these circuits.
Is it the 5030 page?
It is not on the 5030 page. It is in the ECE 1810 page. I could link it up if anybody wants to. Technologies for self-monitoring. That's a huge field, isn't it? I could probably put something together on that. I'm not sure that I can do more than I haven't ever done any of it myself. I mean, obviously, I measure my own blood pressure occasionally and make sure my heart rate is reasonable. But I'm by no means an obsessive self-monitor. I don't have a pedometer on my cell phone or anything like that. You have something specific in mind? I mean, health self-monitoring, obviously.
One thing I wanted to read about this, that people are now using the iPhone, and you're taking data from yourself, putting it that like connects to your iPhone. You can just read off your iPhone. And then measure, heart rate, all kinds of stuff. So what we're doing in class, but
yeah,
I was just curious as to what sensors they use to measure that.
So I don't know. I can find out, I suppose. I know that there's interest in using as many of the cell phone characteristics as possible. Like, can you use the capacitive touchscreen as a diagnostic unit? If you were to spit onto the screen, could you, for instance, could you tell anything about the saliva from the capacitance distribution? Turns out you can. All right. Yeah, it sounds nasty, doesn't it? I mean, smeary. And there's another group. This one boggles the imagination. They build a little a utility that allows you to. It's a snap-on lens that allows you to analyze fecal samples for worms using your iPhone. So you get a poop smear. You put it under your iPhone, and you can tell whether there's worms in it or not, whether the person needs to be treated for worms. That's very cool. It has a huge use.
I saw one device where they hook onto the iPhone, you can put it into your ear and put it inside.
Right. Another good example. Right. It just so there's the camera is rather good. If you can get enough magnification on it as a macro lens or as a microscope, you can do quite a lot. People are working on that. The Android 3 and above allows you to get to the USB port And once you can do that, then you can build custom peripherals that are high speed and pretty nice. And of course, you can always get stuff in through Bluetooth, although that requires a fair amount of energy. It's hard to make it battery powered.
Did you meet in the lab and you could help us out with the final projects and doing this part of
Well, that would be the point, is we'd meet in the lab for final project help, basically. And typically, for the last month of class or so, that's what I do, is we just go down to the lab and then on Thursday just stay there all day. And on Tuesday we have to leave because 2300 wants to use the place. But it gives a couple extra hours to work and some consulting time in the context of real stuff. And the class is small enough that everybody could be in the lab at the same time and still not fill it. So it's kind of nice. I sort of prefer to do that.
You also talk about hearing, vision.
Yeah, I can talk about that, hearing and vision. You're talking more about physiology and less about sort of psychophysics, right? More like how it works rather than what you can see and hear,
Yeah.
although they're related.
Right.
Yeah, we can talk about that. Okay. Do a couple of more lectures anyway then. Okay. See you Thursday.